Hello friends, how are you? I hope you all are well. Today, in this video, I am going to explain how a force acts on a current carrying conductor when it is placed in a magnetic field. It is one of the important concepts of magnetic effects of electric current. So I hope that you all might have subscribed. If you have not subscribed, don't delay to subscribe it, because your subscription will help you to get our video consistently as yearly. Let us start the topic. Here I have mentioned force on a current carrying conductor in a magnetic field. Lorentz observed that when a charged particle placed in a magnetic field in a direction other than the direction of the field, when a charged particle placed in a magnetic field other than the direction of the magnetic field, it experiences a force. I can say that current is nothing but the flow of charged particles. So I can say that a current carrying conductor, that means through which charged particles are in motion, when placed in a magnetic field, it experiences a force, but it must be placed in a direction other than the direction of the magnetic field. Then the current carrying conductor experiences a force. How it is, let us try to understand through a small activity. Let us see. So this is an experimental setup. Experimental setup. This is the supporter, this is the stand. I have suspended one electric wire. This is in a circuit with battery, key and rheostat. Already you know the different parts function. This is a rheostat. It is a variable resistor. By the adjustment, we can vary its resistance. As a result, it can allow different values of current. So this is the thread. With the help of the threads, with the support, I have suspended one electric wire A to C. Now this electric wire is placed in a magnetic field, which magnetic field in this diagram is created by the horseshoe magnet. This is the north, this is the south. You can think this is the north side, this is the south side. So you know that the direction of the magnetic field from north to south, from north to south. This is almost uniform I have drawn. You think that uniform magnetic field. So a current carrying conductor AC, it is placed in between north and south pole of the horseshoe magnet. That means it is placed in a magnetic field, because our concept is force on a current carrying conductor in a magnetic field. In this case, this is the positive side of the battery, this is the negative side. So definitely this is the direction of a current. You can think that this is the direction of the current. This is the direction of the magnetic field. That means this is the direction of the magnetic field. This is the direction of the current. In this case, both are mutually perpendicular, 90 degree. So, when this current carrying conductor placed in a magnetic field, according to Lorentz, how the charged particle experience a force, Lorentz force we say, or we can say that is Lorentz magnetic force also we can say. So the current carrying conductor definite experiences a force. How it experiences force? See here. If the adjustment of a rheostat we make in such a manner the amount of current increases. So definitely here the force experienced by this current carrying conductor also will increase. The current carrying conductor also behave like a magnet. Its surrounding also one magnetic field is there. When current changes, current increases, the strength of the magnetic field created due to this current carrying conductor also increases. Now, the question comes, how does the force act? In which direction the force act? So, the direction of the force acting on this current carrying conductor when it is placed in a magnetic field can be understood by Fleming's left hand rule. Fleming's left hand rule as well as Fleming's right hand rule also we can understand. Fleming's right hand rule also we can use, but the standard law is the Fleming's left hand rule. What is the standard law? See that. This is the direction of current. This is the direction of a current. Direction of the current is the direction of a positive charge. You think this is the positive charge. This is the direction. So, Fleming's left hand rule we can use for the direction of a flow of positive charge. Now you see that. Suppose these three fingers, central finger, forefinger and the thumb are stretched mutually perpendicular to each other. In this case, if the central finger shows the direction of a current, forefinger shows the direction of a magnetic field, then thumb shows the motion of the conductor which is outward. I can represent it by z axis. This is x, this is y, this is z. So this z represents the direction of a force. I have used my left hand. Fleming's left hand rule is applicable for positive charge particles. Now this is the direction of current. Direction of current is the direction of a positive charge. So in this case, if the central finger shows the direction of a current, forefinger shows the direction of a magnetic field, then thumb shows the direction of a force, or I can say that the direction in which the conductor moves. In this case, conductor moves normal to the paper, or I can say the direction of a force is outward. Now, I can also use the Fleming's right hand rule. But in case of Fleming's right hand rule, I have to see the direction of a electron. See that. That is the direction of a electron. In this case, same thing happens. What happens if this one shows the direction of a flow of a electron. This finger shows the direction of the magnetic field. Then thumb shows direction of motion of the conductor or direction of the force. which is the outward. How I explain? Fleming's left hand rule we can apply for in the direction of a positive charge particles, and Fleming's right hand rule I have to consider the flow of electrons or the direction of a flow of electrons. So generally this is the standard rule because it is applicable for positive charge particles. But we can also use Fleming's right hand rule. But if you want to show the right hand rule, then what you have to do? Then we have to show this finger, central finger towards the direction of flow of electrons. This forefinger shows the direction of a magnetic field. Then thumb shows the direction of a force, which is in this case outward. I hope that you might have understood the direction of a force by Fleming's left hand rule or by Fleming's right hand rule. But Fleming's left hand rule is the standard law what we can use. Okay, this is not the standard law. This is the standard law. So I can say that Fleming's left hand rule we can use to find the direction of a motion of the conductor, or we can know the direction in which direction force is acting on the conductor when it is placed in a magnetic field. Now let us discuss when these three are mutually perpendicular. This is the direction of a current. This is the direction of a magnetic field. This direction is the direction of a force. In this case, the current and field are mutually perpendicular. I said that if the current carrying conductor placed in a direction other than the direction of the magnetic field. For example, this is the magnetic field. So the wire should not be placed like this or in opposite direction. In this direction it should not. Except that in any direction. I am not telling this is all the time 90 degree. Any direction other than the direction of a current. Okay? If it is in the direction of the current, then the force will be 0. That's why I am telling, if it is placed in a direction other than the direction of the current or its opposite, then the current carrying conductor experiences a force, which force is called the Lorentz force or Lorentz magnetic force. So now we will calculate the magnitude of force. Magnitude of force. The force is here directly proportional to current. In which case, if this is 90 degree, if the current carrying conductor is placed in a direction perpendicular to the direction of the magnetic field, then the force is directly proportional to strength of the current. If the strength of the current we can vary, the force acting on the carrying conductor also vary. Force is directly proportional to current. Force is directly proportional to length of the conductor, or I can add force is directly proportional to strength of the magnetic field. If I combine these three equations, F proportional to IL B, or I can say that F equal to KIL B, where K is a constant of proportionality. It depends upon the system of units. So in SI unit, B value such that here K equal to 1. If K equal to 1, then F equal to IL B. F equal to IL B. I stands for the current, A stands for the length of the conductor, B stands for the magnetic field. So in this case, I can say that B is equal to F divided by IL. So it is better I shall write up whether it is appearing or not. So we got that F equal to ILB, or I can say that B is equal to F by I into L. In a SI system, force is Newton, current is ampere, Newton. Okay, so this is Newton, this is ampere meter, or we can say Newton per ampere per meter. This is the SI unit of a magnetic field. It is also called Tesla. So the SI unit of magnetic field is Tesla, or we can say this is Weber per meter square. It is also unit of a magnetic field. So this is about the magnitude of a force acting on the current carrying conductor. Here we calculated when the magnetic field and the current carrying conductor are mutually perpendicular to each other. So I hope that you might have understood this concept very clearly. Until the next video, bye.